instructions will also be stored in the memory. So that is also 32 bits. Is okay? Now, out of this 32 bit, 8 bits are kept for opcode and 24 bit are for operand address. Operand address means memory address. So what is the memory address size? Tell me. Be it data memory, be it program memory, what will be the data, what will be the memory size? How many locations will be there? Operand address is 24 bit. So how many locations will be there in the instruction memory? Yes?
2 to the power 24.
2 to the power 24. Simply. That means program memory size will be 2 to the power 24 multiplied by 32 bits. That means there will be 2 to the power 24 locations and each location size will be of 32 bits. That is the program memory size. Is it clear?
Yes, sir. Yes.
Okay. Now 2 to the power 24 means 16 mega. 2 to the power 24 means 2 to the power 20 into 2 to the power 4. That means 16 mega. So program memory size is 16 mega into 32 bits. Same is the case for digital memory. Since each data is of 32 bits, so it will be 16 mega into 32 bits. That is the digital memory size. And analog memory size will be what? Analog memory is not, analog data is not stored in bit form. It will be stored in each sample form. Okay. So analog data memory will be 2 to the power 24. Address will be, locations will be same into one sample. That means 60 mega samples. Stay away. Now, since there are 8-bit opcode, out of that, 1 bit is kept for what? Identify.
Analog or digital?
Analog or digital. So, how many bits are left? 7 bits.
7 bits.
Analog instructions, maximum digital instructions will be 2 to the power 7. Maximum analog instructions will be 2 to the power 7. It's not 5, it will be 2 to the power 7 by mistake. So, both instructions will be of 128. So, 128 plus 128 equal to 256. It cannot be 276. That is maximum. Maximum doesn't mean that you have to consider only 256 instructions. For an example, Intel 8085, it's a 8-bit processor, but it doesn't have 256 instructions. Its total instruction is less than 200. So we have to consider those instructions which are effective and fruitful. Okay. So this is maximum. Maximum doesn't mean that you have to consider just 128 plus 128. Now we have to see how these instructions can be implemented. Next is, whenever we design a processor, we have to decide what are the addressing modes and what are the types of instructions. Addressing modes are direct. Here I have considered. Even I'm telling you, this is a research project. If you feel something else, something more, you can consider it. I am just giving you some broad idea how to design this, what are the things. That doesn't mean that whatever I have written, only you will be restricting yourself to that. Even if you can innovate some new addressing mode is always welcome. Okay? This is a baseline. So typical addressing modes are direct memory addressing, indirect memory addressing, which is very much required, immediate addressing, and registered addressing. I'm not going to discuss all this in details, like why indirect addressing, why, that you can refer to in the standard book, because otherwise it will take more time. Now, type of instructions. So these are the type of instructions. One is the digital analog data transfer. Now, data transfer could be from register to memory, okay, or memory to register, or register to register. Now, memory to memory instructions are not there. If it is required, the data will be transferred from one set of memory locations to another set of memory locations, then it should be done through registers. So first take the data from the memory to register, and then it's shifted from register to another location. Understood?
Yes, sir.
So similarly, analog data transfer, like it can be stored from analog memory to some analog registers or vice versa, or from arithmetic logic unit to analog memory in that way. But data from analog memory to digital memory cannot be transferred directly. Now for that, how it is possible? Let's say some digital analog data I want to store in digital memory. What I have to do?
Quantization.
Look, when the analog data is already stored in the analog memory, it has been quantized and stored. So I want to store, let's say, an analog data to a digital memory. How it should be possible? Now look at this architecture. In the architecture, what you can see, in the extreme right hand side, in the bottom, what you can see, what is the block?
DAC, digital to analog converter.
That means if digital data needs to be stored in the analog memory, first it can go through this DAC.
Yes, sir.
So after that, it can be stored into analog memory,
Yes,
right?
sir.
So
Yes,
here
sir.
it is written to analog data line. So after
Hmm.
conversion, it's coming from the bus, from the digital bus. Okay. So digital data memory that will be converted and stored. Similarly, in the left hand side at the top, what block is there?
ADC.
Hmm?
ADC, sir.
ADC. What is that?
Analog to digital converter. So we need to convert it. Hmm.
Okay, okay. Carry on, please.
We need to convert the analog into digital.
Yeah,
Then we can store it into digital memory.
simple. So now we understand the justification of ADC and DAC in the architecture. Okay. Like when you'll be presenting, the DOE people will ask you every bit of questions I'm telling you from the architecture. You should be
Hmm.
careful about that. Then somebody asked me that how now you should know what is the structure of the analog memory. Okay. So even though I told earlier, I'm just repeating once again, I'm telling you how the analog memory is obtained. Just first, what is that? Oops. No. Can you see this screen? Hmm?
No,
No,
sir.
sir, your presentation is not showing, sir.
Presentation is not? Okay, okay.
Not showing, sir, in the screen.
Okay. Now can you see?
Yes, sir.
Memory. Okay. Now, how this analog data will be stored in the memory. Okay. Now I'll be discussing whenever the relevant thing will come, we'll discuss on that basis. Now analog data. Digital and analog, the difference is, you just see the diagram. Can you see the bottom left hand diagram? There are two
Yes, sir.
diagrams side by side. Can you see them? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Yes.
Yes, sir.
What are the differences between these two diagrams? And these diagrams, what do they indicate?
So continuous analog, discrete analog.
Good. Continuous analog and discrete analog. And here the graph is time versus amplitude, x-axis represents time and y-axis represents the signal strength. So XAT, XA stands for X analog, T is a function of time. So with respect to time at any instant T, XAT will give you the amplitude value. Clear? So this is analog signal, is a continuous. Now this continuous signal you cannot store in a memory. You have to quantize somehow. So that's why what you have to do, you have to sample the signal. First process. So this is a sample. Can you see? Once you are sampling, then the number will be sample number 0, 1, 2, 3, 4, 5, etc. Okay, that means in one instant, what is the signal value? Xn. So y-axis is Xn and x-axis instead of T, we'll call it N. Okay, so, and the sampling time is capital T. So after every T unit of time, the analog signal will be sampled, which is called sampling time. And this sampling time is determined by the Nyquist sampling theorem. Okay, that you must be knowing. So when T equal to, when the sample number is 3, what is the time actually? Actual time is what? When n
ET.
equal to 3, what is the actual time?
3 into capital T.
3 into capital T. Okay. So that now here continuous signals are sampled after every T unit of time. So that means when n equal to 1, n equal to 0, a sample value is there. So this is discrete analog. So this value will be stored in the analog memory. We'll come to analog memory later on. First, let's understand how a signal, because in the natural signals, all will come in analog form. Okay, from analog to digital, the process is there are 3 steps. One is the sampling. Second is
Quantization and encoding.
encoding. Right. So quantization, this process is called analog to digital converter, basically. And coding, because there are different formats. It could be BCD, it could be binary, it could be XS3. So that is the coding. So second part, first part is the sampling part. After sampling, the signal is not digital, mind that. It is still analog signal. So we can call it discrete analog. So now, next question will be how to get it. How we will do the sampling. Theoretically is fine, but practically how we will do it. Okay, in the top there is a symbol. This symbol is what? This symbol is switch. That means after every unit of time, a switch is on, and at that point, you are sampling the signal. What is called it? That means your xt is converted to xn for n equal to 0 to ... 1, 2, 3, 4, whatever it is. Now you have to come for the circuit. Because whatever you are doing, the architecture, ultimately you have to implement in the VLSI form. What is this circuit? Simple circuit. This is a transistor. Now what kind of transistor it is? Arijit? In the diagram, a circuit has been shown. This is a diagram of a transistor. What kind of transistor it is?
It's a PMOS.
It's a PMOS. Okay. Now, here, drain and source, they are interchangeable. Now, in the clock, the gate is connected to a clock. It's a narrow clock. Have you seen that? In the right-hand side, the clock has been given. And this clock will be coming after every T unit of time. You assume that after every T unit of time, a very narrow pulse is coming. So that means whenever this pulse is coming at the gate, the transistor, this is a switching transistor, transistor will be on. Do you agree with me?
Yes, sir.
If the transistor is on, that means the contact between drain and source will be established. The resistance will be 0. That is a switching transistor.
Yes, sir.
That means your whatever is there in Xn, that will be available at point M1. That signal, that is the analog signal at that instant when this clock pulse comes, that signal is available at point M1. Agree?
Yes, sir.
That means it is the discrete analog signal at that instant. So when, if I assume that this clock they are coming at t equal to 0, t equal to capital T, t equal to capital 2t, 3t, 4t, that means n equal to 0, 1, 2, 3 in that way. And just at that point, whatever the input analog signal, that will be available at point M1. Is that agreed?
Yes, sir.
So the sample signals will be available at this. So there is a capacitor. So what capacitor, what is the function of this capacitor?
To hold the value, hold the charge.
This is the charge. So capacitor will be stored and this value will be held in the capacitor. So I can assume that this capacitor is basically a storage unit which is storing the charge at that point. That is equivalent value at particular n will be stored. But before the next value comes, this capacitor has to be discharged. Isn't it?
Yes, sir.
This circuit is known as sample and hold circuit. So it is sampling by this transistor and the data is held in the capacitor. So this is sample and hold circuit. Now, this diagram I showed earlier. In the digital memory, principle of digital and analog, to some extent there are a lot of similarities. Here, let's say this is a switching transistor. Left hand side diagram you see. Okay. A transistor, a capacitor. So here, the data, what is coming, there is a vertical line and a horizontal line. Can you see the vertical and horizontal line in the left hand side diagram?
Yes, sir.
Okay. So, and write, read these signals. These are written. Write means for any memory, there are read signal and write signal. We know read bar, write bar, etc. Okay. If we use a PMOS transistor, we will call it a write non-complement signal. And if it is a PMOS, then it will be complemented. Whatever, let's assume that is a write. If write is 1, this transistor will be on. Agreed? Then whatever the data
Yes,
will be given in the vertical line, that will be coming to the capacitor and capacitor will be stored. The charge will be stored. That means whatever the data is coming from here after sampling, which was there in the capacitor, that will be transferred to this capacitor, I can say. Or if we combine both these circuits, this and this will come here, the stored data will be stored here. And even you can bypass, there are 3 transistors. The middle transistor, you can bypass it. I will explain later on. Directly this capacitor can be connected to the another top transistors in the drain line. So when read signal will be given, then this data will be directly available to the horizontal line, isn't it? Because this transistor will be on upper transistor in the right hand side and directly the data will be stored there. In the middle, there is a transistor has been given for buffering. Buffering because the capacitor and this, a buffer should be there so that the charge cannot be lost. So that means analog data will be stored in the capacitor. If you want to read the data, then what you have to do, read signal should be high, the data will be available in the horizontal line. And if you want to write data, then apply the data on the vertical line, and that data will be stored in the capacitor. Clear?
Yes, sir.
Yes, sir.
So first, once again I am telling you, this is a continuous signal. Continuous signal is coming to this circuit, sample and hold circuit, and it is held in CH register. Okay, this capacitor hold this data. Now, if this data has to be written, then this will be connected to this circuitry. This circuit is a read-write circuit. If you want to write the data, that data will be presented over here and will be stored in the capacitor. And if you want to read the data, directly this data can be read in the horizontal line. So that is the simple one sample storage device. But in reality, there will be many storage. So then how it could be done? Now we know the random access memory. So this is the structure, basic structure of analog random access memory. We all know the random access memory which are used for the digital data storage. Now for storing the data into a memory, we must have to supply the address. Okay, look here, simple structure I have shown. There are 4 locations. For 4 locations, how many will be required? How many address lines will be required?
2.
2 bits. So here A0 and A1. So that means if it is 1024, then 10 address lines will be there. And here a read and write, even though here read write bar, one signal has been shown. Actually, in practice, there will be 2 signals. One is read bar, another is write bar. Okay, if we use read bar, write bar, then those transistors will be PMOS instead of NMOS. Simple thing. So depending on this address, where we want to store the data, one of the row will be selected. So a decoder will be there. So decoder does what? Decoder will be selecting, for an example, address is A0, A1 equal to 00. That means 0th row will be selected. Okay. So if we assume that the top row is a 0, then 1, then 2, then 3, so the first one will be selected. Now here, this diagram corresponds to 4 into 4 bit digital memory. Now here, in our case, we are going to design the analog memory, so there is no question of bit. So in each row, there are 4 blocks are there. Instead of 4 blocks, there is a single block. Each block corresponds to one analog sample storage. Now, what is the analog sample storage? That diagram we have shown. This is the one.
One capacitor is there.
This will be there. This
Yes, sir.
transistor, capacitor, all will be there. This is 1 bit cell, not one sample cell. Bit, in fact, we are used to say bit for digital. Since it is analog, one sample will be stored. So that cell. So instead of 4, only one cell will be there. You forget about the other 4. Only one cell will be there. Okay. So let's say there are 4 samples. Okay. 4 sample means, let's say sample 0, sample 1, sample 2, sample 3, they need to be stored. So that means an analog data 0 to 3. So this sample, how intelligently we are storing? We are first sample and hold circuit is there, analog input. Then first thing will be this one. This is common for all of them. After that, this V0 is connected to what? This is connected to this cell. This cell will store one sample in this capacitor. That's simple. So this is the block, whatever this rectangular block has been shown here, that is nothing but this circuit. Okay. So at the input, what is there? Because this will be coming at the input of, at the top, I1 is there. I2, I3, I4 will not be there, only one bit, I1. So before I1, that is there. Sample and hold circuit. Only one sample and hold circuit. Because at a time, only one sample will be stored. Then this will be stored where? Depending on which one is selected, which row is selected. Now, here, if you see that, if a row is selected, there will be an AND gate, and right signal is there. So depending on that, this gate will be one. So right signal and that particular row. So the output comes to this right, and this gate is selected and data will be stored. That is the structure of the analog memory. Now, is it clear now how the analog data is stored?
Yes, sir.
What about Caprio and Origin? Are you understanding it? What I say?
Yes, sir.
So now, if your location is 24-bit address, so that means your decoder will be more, decoder size will be more complex, and rest of the circuits are same. And in that way, analog data are stored. So it consists of sample and hold circuit at the top, which is not required for digital RAM, but here it is required. So this is also, the difference is analog and digital random access memory. Both deals with the discrete, but only thing in the digital, it deals with the bit. Okay, a number of bits will be there, but here is a sample. That means a sample value, and your decoder will be same for both of them. This structure, one of them will be selected, and decoder, that means a particular row is selected, that will be ANDed with actual read signal, and that will be ANDed with the write signal, and that will come to the gate of the corresponding transistors, and accordingly the data will be stored or data will be read from. Now, please ask me any questions if you want up to this point. Is it okay or?
So what about the Q0, Q1? Actually, these are the output.
Just which one? Oh, these are the output. Here
Bottom.
Q0, Q1, and look, out of these four, only one you should consider, isn't for analog?
Yes, yes.
This diagram
Yes, sir.
is for
Yes, sir.
digital. This is output.
Yes, sir. It is 4-bit digital, but if we if we consider as a analog, then one column will be there.
Only one
Only.
column will be there, right? Absolutely correct. Okay. And
Okay, sir.
again, if we want to make a tri-state bus, then we can use some transistor here. Why this drain and source? Look, any kind of switching things are done by the transistor using the switching property of the transistor. And what? It has three leads, drain, okay? One
Yes.
is a gate, source and drain. So
Source
by
and drain.
controlling the gate, drain to source, either they'll be on or they'll be off. A simple thing, the switch. So gate acts as the switch. Okay? So enable
Okay,
signal
sir.
can be connected to the gate. So if the enable is 1, then the data can be connected to the bus. Is all right?
Yes, sir. Yes, sir.
Simple. Just like your digital RAM. So this is the structure of analog memory, but there is a difference with the digital memory. Now, whenever you access data from the RAM, that data is not lost, isn't it? For an example, when data is transferred in a digital register from one register to another register, say move A, B in the Intel format, the meaning of this is transfer the data from register B to register A, right?
Yes, sir.
Yes, sir.
Yeah. So for that, the data, whatever was there in B, is not going to be lost. Okay. The data of B will be transferred to A. Say, for an example, a register 8-bit register B is having F2, and we execute the instruction move B, A. So A will become F2, but the contents of A will not be lost. It will be as it is. So whenever a data, either from memory or from register, is transferred in the random access memory or in the digital register, data is not lost. But here, in the analog memory, it is based on what? The data is not stored in the flip-flop. Data is stored in the capacitor. So capacitor stores, what capacitor is storing? The charge.
Charge.
Charge. Charge is what basically? Q equal to C into V. We know that. So voltage is stored in terms of charge. And when that charge is transferred, that means the energy is transferred. You cannot create energy. Only the transformation. So there won't be any charge in that capacitor anymore. So each time you
Yes,
access
sir.
memory, the data goes away from the capacitor. So what you have to do?
Restore.
You have to
So once again, we have to charge.
restore it. Okay. That is the basic principle of the dynamic memory, in fact, for digital dynamic memory as well. Because in the digital dynamic memory, basically, uh, data is stored in terms of capacitors. Right? That's why they need to be refreshed.
Yes, sir. Concept of DRAM.
That's what DRAM. Here, this is also the principle like DRAM. Because the capacitor in DRAM, what happens? Not flip-flops. It's a capacitor where the charge is stored. Exactly here also in the
It
analog,
requires refreshing.
it needs to be refreshed. There are two kinds of things. One is in digital data memory, it has to be refreshed periodically after a few milliseconds. Here also you have to do it because some leakage current will be leaked. Another thing is that each time a data is accessed, what you have to do, the same data has to be stored again there. Now this can be done in two ways. Whenever the data is accessed from analog memory, then through A to D converter, temporarily you store in the digital data memory. Okay? After that, you store from there to analog memory. Otherwise, again in the circuit, you have to have some analog kind of register where you have to store. Again from there, you have to store all this kind of thing. So that is why here we have used A to D converter and DTA converter within the processor. Clear?
Yes, sir.
Okay, sir.
So this thing you have to take care of. That means whenever each time an analog data is accessed within the instruction, it has to be embedded that the reverse storage, okay, has been done. That care has to be taken. Now, did you understand the whole thing or not? Please tell me. The
Yes, sir.
mechanism.
Yes, sir. It is
Yes,
clear.
sir.
These are the storage mechanism of analog memory. So what I suggest, one after one, you can design a VLSI design of analog memory. Then your whole project, you cannot do entire thing at a time. You divide into smaller parts, and in the modular form, you do the work. You go ahead. But when we implement our project, we also do in the similar fashion. Okay. We distribute our engineers to do the work in the modular form, and they do it. In this context, let me tell you one thing, uh, especially for the students. Uh, there are more than 1 lakhs of jobs for VLSI engineers in India. And most unfortunate thing is the country is not getting, we don't have enough human resource. Here, in fact, 99% knowledge will not help. It has to be 100%. And India is thinking to borrow engineers, to hire engineers from other countries for our semiconductor plant. Huge number of engineers are required. So I'm telling you, if you can make all these things clear at this moment, then the future will be okay. Otherwise, in fact, I'm telling you, unless the basics or foundations are clear, and all these advanced concepts cannot be made clear. So for this Department of Electronics project, analog memory plays a very important role. So you can design this analog memory in that way. And it's a mixture of, this is a mixed signal processing circuit. The reason being, only analog will not help. Here analog design along with digital is there, because encoder circuits for decoding the address unit. So these compartmentalizations, like I know only digital or I know only analog, this doesn't help. This today's technology require the mixed signals, analog, digital both. So this is the memory design. Now, if there is no other questions, then I can switch back to our earlier design. Is it okay?
Yes, sir. Yes, sir. It's okay.
Just a minute. Then what I will do? I will stop presenting. So these are now here in the extreme left-hand sides. Can you see the diagram?
Yes, sir.
Yes, sir.
Extreme left-hand side, a vertical line. What is this? What this line corresponds? Hmm?
Sir, this is
Analog data memory
analog
line.
memory.
This is the analog data memory line. Analog data memory data line. So it is a line. I'm not calling it bus. Why? What is the difference between bus and a line? Bus is applicable for what? And line is applicable for what?
Bus is applicable for digital data to
Okay.
convert.
Right. That means the bus,
Yes, sir.
each line in the bus carry the information 1 and 0. What is the line here? What we are seeing, analog memory data line. This line will be carrying the analog value, okay, at a particular instant, right? So this must be connected to the analog data memory that is there. So analog data memory, what are the signals required? One is the address. So analog data memory address registers. Can you see? Can you see a box, a rectangle at the top
Yes,
of
sir.
analog data memory, which holds analog data memory address register? So this, what is the function of this register? To hold the address for analog data memory. Simple. So this is
So it is digital data.
hmm?
It is also digital data.
No, not this is address is the address value is
Yes,
the
address is digital. Yes.
digital. So that is going to address this analog memory. And here is the data line, data input and data output.
Yes, it is the analog line.
Okay. So that is connected to the analog line. Another signal line which is not shown here, that you will do it in your diagram. You will correct this thing. So little, because this is a block, block diagram, all the tidbits might not be given. Here some signals have to be given, read and write bus signals, which are coming from the control logic. Okay? Because if you don't give read or write, this analog data cannot correspond. Is it okay?
Okay, sir.
Now, there is a block diagram for memory instruction. This is an instruction memory. Have you seen that instruction memory?
Yes, sir.
Yes, sir.
Now, instruction memory holds what?
Stored the instruction.
It stores the instruction. What is the instruction
instructions?
format? What is the instruction format for this CPU? 32-bit. Each
32-bit instruction.
32-bit. And
8 plus 24.
size will be of 24-bit. Because you have 24 locations will be there. Is okay?
Yes, sir.
So PMAR stands for Program Memory Address Register. What will be the size of this PMAR?
What is the register? 24-bit.
24 bits, right? In fact, I can tell you one thing, you take this diagram in front of you and you start keeping asking you, all these answers you will be getting automatically. So PMAR holds the address. It is basically to hold the address for the instruction memory. And read bar and write bar signals are there in the instruction memory. Can you notice that?
Yes, sir.
Okay. This hash read means read bar, hash write means write bar. Simple. Now, this PMR, whenever you want to access the instruction memory, basically is a program counter which holds the current address of the instruction memory. That's why at the top of it there is a program counter, and program counter size will also be 24-bit. And so program counter delivers its contents to the address bus. That's why it's called program memory address bus, a vertical line. So there it gives, and this comes to the PMAR, and PMAR supplies the address to the instruction memory. Is okay?
Yes, sir.
Now, instruction memory returns the data corresponds to that address given by PMAR. And that should be connected to what? That should be connected to the program memory data bus. What is the size of program memory data bus?
Programming data was 32-bit.
32. That's why
Yes.
this line is 32-bit. You just check it. Program memory data bus is 32-bit. It's connected there. Now from there, where it is coming? To the instruction registers. Okay?
Yes, sir.
So instruction register, out of that, most significant 8-bit will go to the
Decoder.
decoder. That's all these things are shown here. Okay. And if it is required, that depending on the instruction, let's say instruction is load accumulator with some address. So this address was there in the instruction. It was there in the instruction register. So from here, those address will be given to the data memory address bus, and accordingly data will be stored, or data can be retrieved depending on that. Is okay so far?
Sir, I have a question. That is this is the architecture of 32-bit CPU. So the size of the data bus is 32-bit.
Yeah.
So if there is an instruction called immediate addressing mode, then
That cannot be 32-bit. That cannot be 32-bit. That always, will be some 24-bit and 8
24-bit. Yes.
bit by 8. Yeah.
So then
Okay.
how it can be performed, or how this
This 24
suppose
bit.
addition operation,
Hmm. Most
suppose
significant.
ADI.
I understand. I'm telling you. The answer is the most significant 8 bits will be appended by 0. Okay, to make it 32 bit.
Okay, sir.
Now we'll be coming to some crucial point now. So if we understand this architecture, we'll find that as far as the digital instructions are concerned, there are not very difficult tasks. We can do that. But as far as the analog instructions are concerned, depending on that, we have to design the analog arithmetic unit. Okay. Now, analog arithmetic, digital arithmetic unit, it basically it consists of addition, subtraction, multiplications. Okay, in that way, even division we can do by using some algorithm. These are not a very hard job. Now, let's compare digital to analog data one to one. Okay. Analog digital addition and analog addition. Okay, discrete analog addition you can do it directly. Taking the analog to analog data, you can add them, or you can multiply them, etc., etc. You can do, or you can multiply by a constant. Another thing is the differentiation, integrations. These are also very important for analog data. Listen. So how would you do all these things? Analog operations. Even logarithmic operations, which is for analog device, by using the property of analog circuitry, we do the logarithmic operations. Now, what are the first thing for understanding the analog arithmetic unit? We have to understand in details about operational amplifier. Now, operational amplifier is the basic fundamental building blocks for any kind of operation. Operational amplifier, the name has come from that, operational amplifier. It can do operation. Now, what it is capable of doing? Operational amplifier can do addition, multiplications. Now, there are two types of multiplications. One multiplication is constant coefficient multiplications, and another multiplication is multiplying two time domain function. For an example, let's say you are multiplying a sine omega t by 10. Okay, let's say em sine omega t. Em sine omega t is a sine function, and maximum amplitude will be em. The maximum value of sine omega t will be 90 degree, pi by 2. So that is em. Then it will come down and it is like that. And if you multiply it by 10, simply the signal is amplified by 10. Okay. But when one sine function is multiplied by another sine function, there is a different multiplications. Okay. So one multiplication, when you multiply a function by a constant, then in the language of electronics, this is nothing but amplifications. In front of a microphone, when you speak and is connected to an amplifier, it amplifies the signal. It doesn't change the property of the signal. It remains same. Only thing is that its amplitude gets magnified. But when you are multiplying two time domain functions, it becomes a different signal altogether. Its fundamental characteristics is not there. So this multiplication is different. And in electronics, we call it modulation. This multiplication
Modulation.
is known as the modulation. So how these two time domain functions are multiplied, that we have to know. Now, analog devices, I think in the next class, I will discuss about operational amplifier. This will be required here. And operational amplifier, my emphasis will be how this operational amplifier can be tuned for arithmetic operations. Now here one thing you notice, excuse me, for digital arithmetic unit we call it ALU. ALU stands for arithmetic and logical operation, arithmetic and logical unit. But for analog we call it only analog unit, because analog logical unit, at least to my knowledge, it is not there. Okay,
Logical means it should be digital, na?
it should be digital. So that's why I called it analog AU, analog unit. Okay, analog arithmetic unit, AU arithmetic unit. So to understand these arithmetics, what we will be discussing, how to do addition, subtraction, constant coefficient multiplications, time domain functions multiplications, and integration, differentiations, and what else?
Amplification?
No, amplifications, yeah.
Actually multiplication, huh?
Constant coefficient multiplication is the amplifications that is there. Okay. Then another thing is very important. When you do integration and differentiations, integration is very easily done by capacitor circuits. And differentiations also can be done by capacitor in a different way altogether. Now, integrations and differentiations, these are done using the physical properties of the devices. Now, what are the physical properties of the devices? If we see the capacitor, what is the physical property of the capacitor? It stores the charge. That means it accumulates the charge. The charge accumulation is basically integration. What? Vc equal to Q equal to C into V. We know this formula. Charge accumulation in a capacitor is given by Q equal to Cv. So V equal to Q by
Yes,
C.
sir.
So 1 by Cq means what? Integration of I dt. That means the capacitor has the integration property by itself. Now, what is the inductor? Inductor is based on the Faraday's laws of electromagnetic inductions. E equal to L di dt. The induced voltage is equal to L into rate of change of current, which comes from the rate of change of flux. So E equal to L di dt, this has got, that means the inductor has a differentiator property. Listen, it's doing the differentiations. Resistor has the linear property, V equal to I into R. So we need all these devices. But unfortunately, when we're designing the VLSI circuits, in a VLSI circuit, making an inductor is not a trivial task. It will take huge area and huge power consumptions. It's absolutely impossible to implement inductor within a VLSI chip. So with the designer, what we do, we find out some indirect technique to use the inductor. So inductor can be done using the capacitances. That's a very interesting thing. And using operational amplifier, the capacitance can be like connecting a capacitance in proper form, and inductor can be built. That is the way it is done in the modern days for VLSI design. And another thing is very important is when we design any high-speed processor, it needs a very high clock frequency. Now, high clock frequency, if we generate outside, for an example, some gigahertz and all, then due to electromagnetic induction interference, it will spoil totally. So what you have to do, inside the chip, you have to generate this high frequency. In the question, inside the Chiefly if you want to generate the high frequency, how to do it? Again, we use the theory of signal processing. How you generate a comparatively, relatively low frequency square wave that can be generated always using RC circuit. Now, if it is a square wave, that means it's a periodic signal. And if the signal is periodic, it has, according to Fourier series, it has infinite number of sine and cosine harmonics and a DC component. So you take the higher harmonics from that, but the level will be very low. Then amplify that and filter out the other signals. In that way, the high frequencies are generated in the most modern VLSI circuits. So, truly speaking, today when we design a processor architecture, at least 3 to 4 subjects are directly related with that. One is the domain knowledge of the architecture, then thorough knowledge of the analog circuitry, then the VLSI design that will be required, and most importantly is the signal processing. So while discussing these things, we'll be discussing, taking this example, and whenever, whatever is required, we'll shift to that, discuss these things, and again we will come back. Is all right?
Yes, sir.
So that is the essence of the project. So that's all for today. Okay. Now, if you have any questions.
Sir, I have a question, sir. Sir, as you told about the inductor, so when I used to design the analog circuits, I have realized the resistor as a MOS device. So my question is, how can I realize the inductor with
I
MOS
told you
device? Is it
that I'll be
possible?
discussing when I'll be discussing the operational amplifier. Okay?
Okay, sir.
Step by
Okay.
step we'll be doing. Okay.
Sir, another operation that is logarithmic operation.
Okay, logarithmic
Then
operation.
which
Okay. That is done by, again in the operational amplifier I will discuss, but I'm telling you, since you are asking, in the operational amplifier, if you connect in the feedback path, okay, you assume that there are two inputs. One is a inverting input, another is the non-inverting input, one is the output. Is okay? So these are the three leads of the operational amplifier. I'm not considering the power supply and all. So let's say in the forward path there is a resistance R1, and in the feedback path there is a resistance R2, and output is V0. Input is V in. So V0 will be equal to minus R2 by R1 into V1. We agreed?
yes, sir.
Now instead of resistance, you use a diode. Now what property diode has? Diode has the current and voltage. That relation is what? Is a nonlinear. And this relation,
Non-linear.
if you just go through it, it is a logarithmic. It followed ln, isn't the current and voltage? So if we use
Okay,
that
sir.
diode, so automatically output will be proportionate to the logarithmic of the input. Now, if you want to multiply two numbers, A and B, how do we do? Log of A into B equal to log A plus log B.
Log A plus log B.
So you take log A, one operational amplifier, logarithmic amplifier, output will be log A. Another operational amplifier, it will be log B. Then you add them by using another operational amplifier, third operational amplifier, output will be what?
Log AB.
Log of A plus log B equal to log AB. Then you use another inverse, then you will get AB. And inverse means the diode will be in the forward path and resistance will be in the feedback path. So you're ready. That is the way of doing two time domain multiplication functions using operational amplifier. Is okay?
Yes, sir. Yes, sir. Thank you, sir.
So we'll discuss in details about operational amplifier now. Like from the practical point of view and how these mathematical operations can be done using operational amplifier. Then another thing, you have to understand the signal processing also. Otherwise, in fact, this kind of huge project cannot be implemented. Because the moment you will come to analog, you have to know that discrete analog signal processing. That's very important. And as far as the neural network is concerned, for artificial intelligence, without signal processing, you simply can't deal with artificial intelligence. The reason being, most of the major applications of signal processing is involving the image processing, speech processing, and all. And when you talk about the image video cannot survive without audio. So both signal processing, image processing, 1D and 2D, these are required for more and more functions will be included in the analog. And then for this artificial intelligence, what are the mathematical things, especially for convolution neural network, what mathematics we have to adapt over here, we'll slowly will go into that. Now this architecture is a very basic architecture. At the top of it, once we understand this thoroughly, then we'll enter into the reconfigurable that will add with this architecture. So the architecture will consist of two parts. One is the static, another is dynamic. Static is the static instruction set. Based on that, it will be done. So static has two parts. One is the analog, another digital. And configurable part, configurable analog, configurable digital. This will be there. So in that way, the whole thing will be done. So it will be a very complex processor, but it will not be at all a complex if we just go ahead step by step and make your milestone. In the project report, I have done the inter milestone. You can follow that thing and start doing the work. Then I don't think there will be any problem. After that, when you'll be when your design is settled and finally you are going to implement, then you have to decide what technology you will be using, what submicron technology will be used. That depends on what are the complexity of overall circuitry, analog, digital. Then what is the maximum speed it can handle, and from that the timing will be coming. Now for this timing, whether that technology can permit or not, that again depends on many other things. For example, the forward path of the transistors, the reverse, all these things, it depends on the distance between drain and source. So lambda principle has to be applied for realistic design. Now, in the physics of electronics, physics of this, you must have studied that when your drain and source, like 2 p-type or n-type is there, and there is a gap in between where the charge will be flowing. So what should be the minimum gap of that? And what is that? And there is a formula which I discussed in the I think VLSI design class. You can refer to those class notes. Things are there. So if you can complete this project, you will be learning 6 subjects very thoroughly. Okay?
Sir, I have a query, sir. Sir, this is a big project, and you have told that we have to choose the technology at the end. So also you have mentioned that we
Not
have
at the
to.
end, when you design, this part will be completed, then you have to decide which technology you will be going. Then you have to adjust. Again, I'm telling you, from my past experience, I'm telling you, then you have to adjust. Let's say the latest technology what is available with that, it's not possible to accommodate at this moment. Then slightly, all that you have to do, instruction set, slightly you minimize it, again you do it. In that, this trial and error has to be done.
Okay. Sir, with your permission, I would like to ask one thing. Sir, then first we will find out the instruction set, we will complete that part. After that, we will divide it and design the analog memory part, what you have mentioned today, analog memory part and other parts. We, by that way, we should approach, or we should start from the beginning. As you have mentioned, we have to design analog memory part and ALU part, analog.
Vivek, all these things,
Has.
next day I'll discuss. Okay.
Okay, okay, sir.
Okay. So So this understanding I started. So next I'll tell step by step.
Okay, thank you, sir. Thank you very much,
Thank you,
sir.
sir.
Thank you,
If
sir.
you're, sir, are you there, sir?
Yeah, I'm here. But the thing
Sir,
is
if
that
your
I will
health
not be
permit,
available from the next month. Maybe July sometime, up to sometime I'll be here, but then I will not be here. I might have to go to Singapore,
so,
and from there I'll go to US and Canada. Both.
oh, sir, then for that can we arrange classes frequently?
Uh, let's see. Next Sunday, let's come. After that, I'll see, depending on my health. Okay.
Okay, 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 sir. And another thing, sir, Origit have prepared a document with the instruction set. Should I send it to you? That
No, don't send it to me. In fact, next day when I will meet, I will discuss, because we
okay,
have
okay,
so many other things to do. I might not get the time unnecessarily to be. Okay.
okay, sir.
Okay. Thank you very
Okay.
much. Thanks a lot.
Thank you, sir. Thank you.
Thank you, sir.